At first glance, it feels like pure, instantaneous magic. You type a random, messy number into your pocket calculator, hit the sign button, and before your finger even leaves the plastic, a highly precise 10-digit decimal pops up on the screen. But this isn't magic. It is completely real, mathematically calculated, and relies on a brilliant algorithmic trick that you were almost certainly never taught in school. Say hello to the CORDIC algorithm. If this acronym sounds completely alien to you, it's probably because we all remember a very different high school math class. We remember the teacher standing by the whiteboard, drawing right triangles and hammering the classic formula we memorized until it was permanently ingrained in our brains. The sine of an angle is simply the length of the opposite side divided by the hypotenuse. Most of us accepted that original, geometric definition as absolute truth, without asking too many questions. But what if I told you that this mathematical reality completely falls apart the moment you look inside your calculator? If you pay close attention to the device in your hand, you'll notice a glaring logistical problem. A microchip doesn't own a ruler. It cannot draw a physical triangle in the silicon, measure the physical lengths of the sides, and divide them. So how does it actually know the answer? How can a tiny piece of plastic, powered by a single battery and equipped with incredibly limited memory, figure it out so flawlessly? Let's dive in step by step and discover the engineering magic behind the machine. To understand how we actually arrive at the answer, we have to look at how pure mathematicians usually solve this without a triangle. If you ask a math major how to calculate sine from scratch, they will probably point you to an ancient, clever algebraic trick called the Taylor series. It is an infinite polynomial equation that allows you to calculate trigonometric functions using basic arithmetic. It looks like this. The sine of x is equal to x minus x cubed divided by 3 factorial, plus x to the 5th power divided by 5 factorial, minus x to the 7th power divided by 7 factorial, and so on. In theory, it's beautiful. You just keep subtracting and adding increasingly complex fractions until you get a precise enough answer. But theory is nice. The real question is, does this actually work in practice for a cheap pocket calculator? This is exactly where we hit the trap. The problem in the computer world is that a basic calculator, especially the early digital calculators of the 1970s, has an incredibly weak processor and strictly limited physical memory. Doing massive multiplications, calculating exponential powers, and dividing by giant factorial numbers over and over again requires an immense amount of processing power. In the world of computer science, multiplication and division are expensive operations. Calculating a long Taylor series for every single keystroke would cause a massive delay, completely drain the battery, and overheat the tiny processor. So now you are probably sitting there asking yourself, if the standard math formulas are too heavy, what on earth is the calculator actually doing behind that screen? This is where the real algorithmic trick kicks in. Programmers and computer scientists use the CORDIC algorithm, which stands for Coordinate Rotation Digital Computer. Invented in 1959 by Jack Vulder to help navigate military bombers in real time without heavy computing hardware, it is a masterpiece of efficiency. Instead of rushing to do a massive, dangerous calculation with heavy multiplication, the computer skips the complex algebra completely. Instead, it relies on a tiny, hard-coded cheat sheet and a game of hot and cold. Let's break it down. Imagine you want to find the sine of 42 degrees. The calculator doesn't try to solve 42 degrees all at once. Instead, it acts like an airplane pilot trying to lock onto a radar target through a series of course corrections. The calculator memorizes a very specific shrinking list of angles. Why those magic angles? There's a brilliant reason for why it chooses these exact numbers, which we'll see later. Step 1. The calculator starts at 0 degrees. Since 0 is lower than the target of 42 degrees, it steers up by adding the first magical angle of 45.0 degrees. This brings its current position to 45.0 degrees. Step 2. Now at 45.0 degrees, it has overshot the 42-degree target. It needs to steer down, so it subtracts the next angle on its cheat sheet, 26.6 degrees. This drops its position down to 18.4 degrees. Step 3. Sitting at 18.4 degrees, the calculator is too low again. It steers back up by adding 14.0 degrees, bringing the new position to 32.4 degrees. Step 4. At 32.4 degrees, it is still below the target. It steers up once more, adding the next angle of 7.1 degrees. This pushes its position up to 39.5 degrees. Step 5. Still slightly too low at 39.5 degrees. It steers up again by adding 3.6 degrees. This causes it to overshoot the target slightly, landing at 43.1 degrees. Step 6. Because 43.1 degrees is higher than 42, the calculator corrects its course and steers down by subtracting 1.8 degrees. This brings it very close to the target, settling at 41.3 degrees. Step 7. At 41.3 degrees, it is just barely under the target. It steers up by adding 0.9 degrees, nudging its position to 42.2 degrees. Step 8. Since 42.2 degrees is just a tiny bit too high, it steers down one last time in this sequence by subtracting 0.4 degrees. This brings the current position to a very close 41.8 degrees. It keeps zigzagging, adding and subtracting smaller and smaller preset angles from its list, swinging left and right, getting closer and closer until it perfectly lands on your 42 degrees. Let's look at another example to see how incredibly robust this algorithm is. What if we want to find the sine of a steeper angle like 71 degrees? Step 1. We start back at 0 degrees. Since 0 is lower than 71, we rotate counterclockwise by our first magic angle of 45.0 degrees. Step 2. Sitting at 45.0 degrees, we are still too low. So we add the second magic angle on our list, 26.57 degrees, rotating counterclockwise again. This brings us up to 71.57 degrees. Step 3. Whoops, we just slightly overshot our target of 71. To correct course, we rotate clockwise by the third magic angle, subtracting 14.4 degrees. We drop down to 57.53 degrees. Step 4. Now we're too low again. We steer counterclockwise by 713 degrees, climbing up to 64.666 degrees. Step 5. Still too low. We add 3.58 degrees, bringing our vector to 68.24 degrees. Step 6. Still need to go higher. We add 1.79 degrees, reaching 70.3 degrees. Step 7. Almost there. We add 0.90 degrees, inching up to 70.93 degrees. Step 8. We are incredibly close. We add the final magic angle of 0.45 degrees, landing at 71.38 degrees. Just like before, with each step, the swings become smaller and our vector h1's in right on our target. Now let's try one more. How about a much smaller angle, say 15 degrees? Watch what happens. Step 1, we start at 0 degrees. 0 is smaller than 15, so we add our first magic angle of 45.0 degrees. We immediately overshoot our target by a huge margin. Step 2, no problem. Our algorithm just corrects course. Since 45.0 is much higher than 15, we rotate clockwise, subtracting the second magic angle of 26.57 degrees. This brings us down to 18.43 degrees. Step 3, we are still slightly too high. So we rotate clockwise again, subtracting 14.4 degrees. Our vector drops all the way down to 4.39 degrees. Step 4, now we're too low. We steer counterclockwise, adding 7.13 degrees, which brings us back up to 11.52 degrees. Step 5, still too low, so we add 3.58 degrees. We climb to 15.10 degrees, slightly overshooting our target again. Step 6, we correct by rotating clockwise, subtracting 1.79 degrees. We settle at 13.31 degrees. Step 7, we're too low, so we add 0.90 degrees, moving up to 14.21 degrees. Step 8, still slightly low, we add 0.45 degrees and land safely at 14.66 degrees. Notice a pattern? It doesn't matter if the target is 42, 71, or 15 degrees. The CORDIC algorithm blindly follows the exact same set of rules, completely avoiding any complex algebra, and always manages to zigzag its way perfectly to the answer. Okay, we've successfully steered our vector to perfectly match our target angle. But you might be wondering, wait a minute, where's the actual sine value? Until now, we've only been talking about rotating a vector back and forth. But remember, the sine of an angle isn't the rotation itself. It is specifically the vertical height, the y-coordinate of that vector. We know exactly where the vector is pointing, but without using any complex math, how on earth does the microchip actually calculate that exact y-coordinate? To answer that, we have to pull back the curtain and look at what is mathematically happening to the x and y coordinates when we rotate a vector. If you take a vector with coordinates x, y, and rotate it counterclockwise by a certain angle, the standard mathematical formulas to find its new position look like this. The new x-coordinate is x times the cosine of the angle, minus y times the sine of the angle. The new y-coordinate is y times the cosine of the angle, plus x times the sine of the angle. And if we want to rotate clockwise instead, the formulas are almost exactly the same, but some of the plus and minus signs flip. The new x-coordinate is x times the cosine of the angle, plus y times the sine of the angle. The new y-coordinate is y times the cosine of the angle, minus x times the sine of the angle. But wait, take a really close look at those formulas. Do you see the massive glaring problem? To calculate the new coordinates and rotate our vector, the formula strictly requires us to multiply by the sine and cosine of our rotation angle. We are trying to build a calculator that finds the sine of an angle. But to do that, we literally need to already know the sine and cosine just to rotate the vector in the first place. It seems like an impossible chicken and egg problem. We need sine to calculate sine. But this is where the CORDIC algorithm pulls off its greatest mathematical magic trick of all. Watch what happens if we take out our mathematical scalpel and factor out the cosine term from the equations. The formulas suddenly transform into this. The new x-coordinate becomes the cosine of the angle multiplied by the quantity, x minus y times the tangent of the angle. The new y-coordinate becomes the cosine of the angle multiplied by the quantity, y plus x times the tangent of the angle. Notice that the sine term has completely disappeared, replaced by a tangent term. But we still have that pesky cosine sitting at the front, threatening to ruin our simple calculator with complex decimal multiplication. So, what if we just ignore it? If we completely drop the cosine term from the equation, we aren't performing a perfect, rigid rotation anymore. By ignoring the cosine scaling factor, the vector will actually stretch and grow slightly longer with every single step. But crucially, it will still point in the exact same direction. If we throw away the cosine, our rotation equations become beautifully simple, a counterclockwise. The new x is simply x minus y times the tangent of the angle. The new y is simply y plus x times the tangent of the angle. Clockwise, the new x is simply x plus y times the tangent of the angle. The new y is simply y minus x times the tangent of the angle. This looks much better, but there's a catch. We still have to multiply our coordinates by the tangent of the angle. And remember, multiplication is an expensive operation that drains battery and slows down the microchip. This is the exact reason why the CORDIC algorithm uses that specific, hard-coded list of magic angles. Jack Volder didn't just pick random numbers out of a hat. He specifically engineered his cheat sheet so that the tangent of every single angle is a perfect having fraction. The tangent of 45 degrees is exactly 1. The tangent of 26.57 degrees is exactly 1/2. The tangent of 14.4 degrees is exactly 1/4. The tangent of 7.13 degrees is exactly 1/8. In the binary language of a computer, multiplying by a power of 2 isn't actually a math operation at all. It's just a bit shift, moving the decimal point over by one spot. It is instantaneous and requires almost zero processing power. And that is where we will pause for today. We've completely dismantled the impossible chicken and egg problem, factored out the cosine, and replaced complex multiplications with instantaneous bit shifts. You now have every single mathematical puzzle piece sitting right in front of you. So, I have a challenge for you. Can you figure out how to put these pieces together to build the rest of the algorithm by yourself? You have all the tools you need to do it. How exactly does the microchip use these magic bit shifts to zoom in on any target angle and pull out the sine? Grab a piece of paper, try to write out the loop, and let me know what you come up with down in the comments below. I read every single one, and I'd love to see your theories. If you enjoyed this deep dive, make sure to hit that subscribe button and ring the bell so you get notified the second part 2 drops. Next time, we'll put the algorithm to the ultimate test, trace through the actual loop step by step, and finally conquer that pesky cosine stretch factor we left behind.